COMB-SORT is a sorting algorithm discovered by Stephen Lacey and Richard Box in 1991. COMB-SORT improves on bubble sort, and hence falls under the class of comparison sorts. The main idea for this type of algorithm is to eliminate the small values near the end of the list, as these slow down the bubble sorting process. Large values at the start of the list are usually not a problem. Similar to shell sort, an idea of gap is introduced for COMB-SORT. A gap is defined as the distance between two items in a list. The gap starts out as the length of the list, being sorted divided by a shrink factor. Elements separated by that gap are compared, and are swapped, if necessary. Then, the gap is divided by the shrink factor again. This compare and swap process happens again with this new gap, and the entire process repeats until the gap is 1. At this point, COMB-SORT continues using a gap of 1 until the list is fully sorted. The final stage of the sort is thus equivalent to a bubble sort. However, the smaller values at the end of the list have been dealt with, so a bubble sort will be efficient. The shrink factor is crucial, because a small value means that it would be slower for the gap to degrade to 1, which means that more comparisons have to be made, slowing down the process. A large value will not effectively eliminate the small values near the end of the list, as not many comparisons would be made. Lacey and Box empirically found, by testing COMB-SORT on over 200,000 random lists, that a shrink factor of 1.3 is the most effective for this purpose. With this explanation, let's look at a simple simulation of COMB-SORT. We first initialize 2 pointers separated by a distance as defined by the gap. Gap is initialized to be the input array length divided by 1.3. Now, since the second pointer points to 16, which is smaller than 91, a swap is made to partially sort the array. Then, both pointers move 1 position to the right and ensure that the second pointer always points to larger value than the first pointer. This continues. Once the second pointer reaches the end of the array, gap is divided by 1.3. The pointers are initialized to the start of the array. They then move across the array in the same fashion as before. This occurs again and again. Now, let's have a deeper insight by looking at the Java code for COMB-SORT. First, we see the gap being initialized to the input array length divided by 1.3. Swapped is a boolean that allows us to keep track of whether any swaps occurred in the iteration. We also see that the sort or the while loop runs as long as the gap is larger than 1, or when swapped is true. The boolean swapped helps reduce COMB-SORT to bubble sort when gap is 1. It ensures that the while loop runs until the entire list is sorted. The for loop essentially represents the 2 pointers we saw earlier, running across the array. The if statement checks if the first pointer points to a larger value than the second pointer. If so, the elements are swapped. Swapped is then set to true. Now, let's analyze the performance of COMB-SORT. The worst case complexity of COMB-SORT is O(n) squared. This occurs for a gap size of 1 and a shrink factor of 1. In this case, COMB-SORT reduces to a bubble sort, which results in the worst case complexity. The average case is n squared divided by 2 to the power of pp is the number of iterations of COMB-SORT. The proof of this utilizes complexity and information theory, which is beyond the scope of the module. The best case complexity is n. This occurs when the array is already sorted. The space complexity is also a constant, as no other data structures are needed. This sort is also not stable. A sorting algorithm is stable if the relative order of duplicates is preserved. However, due to the concept of gap in COMB-SORT, non-contiguous elements are swapped, resulting in the instability of the sort. That's it for today. Thanks.